This training will present an overview of the new 802.11ax standard, which is the 6th generation of Wi-Fi and rebranded by the Wi-Fi Alliance as Wi-Fi 6. 802.11ax is the new 802.11 standard that will bring Wi-Fi improvements into enterprise, small, medium business, and commercial Wi-Fi wireless LANs. We'll start out with a very high-level overview of the building blocks of 11ax, then drill down deeper into each building block. This will include a discussion on Ofdm, Ofdm versus Ofdma, Ofdma versus multi-user Mimo, long Ofdm symbol, 1024 QAM, BSS coloring, target wake time, IEEE, Wi-Fi Alliance, and commercial activities, and we'll finish up by talking about some use cases. Before discussing 11ax, let's briefly take a little trip through the evolution of Wi-Fi. 802.11 has evolved over the past 20-plus years. People have been working on this since the early 1990s. The first standard was published in 1997, and 20 years later we are getting ready to ratify 802.11ax. It has not yet been ratified, but just like what happened in the past, as a new standard is approaching ratification, products are manufactured and sold before the standard is ratified. Changes that will go into the standard beyond this time can all be accommodated through a software change, which is how the process works. The other thing I want to highlight is the operating band. The standard started with 2.4 GHz. Then with 11n, it supported both 2.4 and 5 GHz. 11ac only supported the 5 GHz band because the thinking was to encourage people to move towards 5 GHz because it was a much cleaner frequency. With 11ax, both 5 GHz and 2.4 GHz are supported. One big factor in this is the proliferation of 2.4 GHz IoT devices that are coming on the market today. Also, the FCC in the United States is opening the 6 GHz unlicensed spectrum for Wi-Fi. 11ax will be the first standard that will be applicable for 6 GHz as well. For channelization, the standard started with 20 MHz and was expanded to 40 MHz in 11n and up to 160 MHz in 11ac as well as 11ax. Today, we see very little 160 MHz applications, but with 6 GHz, this might become a reality. The peak PHY rate started with 2 megabits per second, and with 11ax, we're talking about up to 10 gigabits per second for a wireless medium. People talk about high throughput, but what really matters is how well we utilize the spectrum. High throughput sells products because it's easy for everyone to understand, but what really matters is how well the standard uses the available spectrum. This is measured by link spectral efficiency. The first standard could push 0.1 bits per second per hertz. Today, with 11ax, we're pushing 62.5 bits per second per hertz. The standard is becoming more efficient in utilizing the available spectrum. This is what matters most. How often are we going to be in a situation where we really need 10 gigs? The overall spectrum performance is also indicated by the name of the standard. 11n is called HT, or high throughput. 11ac came along and was called VHT, or very high throughput. 11ax is called HE for high efficiency. Efficiency is the big thing in the new standard. Another metric was the maximum number of single-user streams. The original standard had one transmit chain and one receive chain that allowed us to transmit one stream of data. Then 11n came along with 4 radio chains. Now we could transmit 4 parallel streams to the same device, which improved throughput and efficiency. 11ac allowed as many as 8 streams, which required us to build APs and clients with 8 radio chains. However, with both 11ac and 11ax, although we can transmit up to 8 streams to a device, you also need a client with 8 radio chains. You can do this with APs as they are larger and powered with a dedicated power source, but clients are small and battery operated. Wi-Fi manufacturers don't build 8-chain clients. Clients usually have only 1 or 2 chains. So even though I have 8 streams on my AP, a client may only be capable of 2 streams. So the multi-user Mimo concept came along with the idea that if the AP can transmit 8 streams, why limit it to transmitting all 8 streams to one device? Why not multiple devices? We can break those 8 streams into 4 groups of 2 streams and send them to multiple 2-stream devices, such as a smartphone with 2 streams capability. That's essentially the multi-user concept. 11AC allows the AP to talk to 4 devices at the same time. 11AX extends this to 8 devices. With 11AC, we were able to do multi-user MIMO only in the download direction. With 11AX, you can do multi-user MIMO in both the upload and downlink directions. 11AX introduced a new modulation scheme called Orthogonal Frequency Division Multiple Access, or Ofdm. This is new to Wi-Fi, but has been in use in other standards, especially LTE, where it works very well. The concepts that have been proven in LTE are now being integrated into Wi-Fi. 11AX also added a modulation scheme of 1024 QAM, which allows us to do higher data rates. The maximum number of OFDM tones is increased from 64 in 11N up to 2048 on a 160 MHz channel in 11AX. And the subcarrier spacing has been reduced by 4 times from 312.5 kHz to 78.125 kHz. The narrower subcarrier spacing allows better equalization and enhanced channel robustness required for outdoor operation. We'll discuss many of these features in much more detail through this training, but as you can see, Wi-Fi has evolved tremendously over the past 20+ years. In the past, wireless LANs focused on theoretical peak speed. With 11AX, even though the speed will increase over 11AC, the emphasis is on overall network capacity and efficiency, not just speed. 11AX is the next evolution of the IEEE 802.11 Wi-Fi standard and will become prevalent in very dense environments, such as urban apartment complexes, college campuses, concert venues, or sports stadiums, where many clients will access the internet over Wi-Fi. The IEEE standard is currently in development and is expected to be publicly released in 2019. For 802.11n, the maximum theoretical speed was 150 megabits per second per stream. 11AC increased this to a theoretical speed of 866 megabits per second per stream, which was over a 6-fold increase. 11AX will increase the speed up to 1201 megabits per second, which is faster, but not the 6-fold increase like 11N to 11AC. Though the nominal data rate is just 37% higher than 11AC, the new amendment is expected to achieve a 4 times increase to the average user throughput due to more efficient spectrum utilization and improvements for dense deployments. Better speed is not the most important issue. The maximum speeds are notoriously inaccurate in the real world. Performance can vary widely based on range, obstacles, other signals in the air, multipath reflections, and the quality of your access point and your client device. To address these issues, 11AX aims to improve efficiency in a number of ways to give you consistently higher real-world speeds than what you would get with 11AC. Perhaps the biggest change is a feature called Orthogonal Frequency Division Multiple Access, or OFDMA. 802.11x uses 4G LTE's proven and foundational OFDMA technology for efficient access. This OFDMA technology allows multiple users with varying bandwidth needs to be served simultaneously. What it does is chop up each wireless channel into many smaller partial channels. This allows up to 9 different clients to talk to the AP at once over a single 20 MHz channel, 18 over a 40 MHz channel, 37 over an 80 MHz channel, and 74 over a 160 MHz channel instead of just 1. Through these smaller channels, the AP gets more flexibility, allowing it to allocate bandwidth to each device based on its data needs. This helps to increase overall network performance. OFDMA also works in tandem with multi-user MIMO. The gist of this is that multi-user MIMO allows an AP to address multiple devices simultaneously instead of one at a time sequentially. Multi-user MIMO was introduced in 11AC, but only in the downlink mode. 11AX supports up to 8x8 multi-user MIMO in both downlink and uplink modes, which allows it to serve up to 8 users simultaneously for a significant capacity boost. Multi-user MIMO also benefits the performance of legacy devices such as 802.11ac Wave 2 and older devices to improve every device's experience. Another 11AX feature is the addition of color. 11AX supports a feature called Basic Service Set or BSS Color, which is a 6-bit identifier that is attached to each PHY header to indicate what wireless LAN it came from. Since Wi-Fi is a half-duplex medium, meaning that only one radio can transmit on a frequency domain or channel at any given time, an 802.11 radio will defer transmission if it hears the PHY preamble transmission of any 802.11 radio at a signal detect or SD threshold of 4 decibels or greater. This is referred to as medium contention overhead. In high-density venues, such as a stadium or large conference rooms, this problem becomes more acute because of the number of APs and clients. Unnecessary medium contention is referred to as overlapping basic service set, or abbreviated OBSS, also commonly referred to as co-channel interference, or CCI. 11AX was tasked with addressing the OBSS challenge by improving spatial reuse, which is often referred to as BSS coloring. This mechanism was originally introduced into 802.11AH to address medium contention overhead due to OBSS. It assigns a different color, a number between 0 and 63, which is added to the PHY header of the 802.11ax frame to each BSS in an environment. With BSS color, an AP can identify which frames are coming from other networks and ignore them as long as they are below a threshold of weakness to prevent interference and should help avoid unnecessary slowdowns. Target Wake Time, TWT, is another concept developed in 802.11AH. It allows devices to negotiate when and how often they will wake up to send or receive data. TWT increases device sleep time and in turn substantially improves battery life, a feature that is particularly important for IoT devices. This allows the Wi-Fi transponder to sleep when the transmission isn't necessary, which should help to preserve precious battery life once 11AX devices are available. In addition to saving power on the client device side, Target Wake Time enables wireless access points and devices to negotiate and define specific times to access the medium. This helps optimize spectral efficiency by reducing contention and overlap between users. Although the primary goal of 11AX is better efficiency, more speed isn't a bad thing. Quadrature Amplitude Modulation, abbreviated QAM, uses both phase and amplitude of an RF signal to represent data bits. 11AX will support 1024 QAM and new modulation encoding schemes, or MCSs, that define higher data rates, which translates to better throughput and 25% higher capacity with 10 bits per symbol versus 8 bits in 256 QAM, which is used in 11AC. More bits equals more data, and the payload delivery of data is more efficient, like having a bigger truck. 11AX also introduces 2 new modulation coding schemes, MCS10 and MCS11, which will most likely be optional. 1024 QAM can only be used with 242 subcarrier resource units, or RUs, or larger. This means that at least a full 20 MHz channel will be needed for 1024 QAM. When wireless devices transmit a signal, the RF signal reaches the destination receiver directly and by reflections off walls, ceilings, and other obstacles. This is referred to as multipath. The Ofdm symbol was originally designed with indoor Wi-Fi in mind. Multipath reflected RF signals were expected to reach the receiver very quickly. The Ofdm symbol was composed of guard intervals followed by a data portion, then another guard interval, and then another data portion area, and so forth. The guard interval was either 0.4 or 0.8 microseconds, with the useful Ofdm data portion set at 3.2 microseconds. When using Wi-Fi outside, the guard interval needs to be increased to compensate for longer distance reflections. 11AX long Ofdm allows up to a 3.2 microsecond guard interval, with the data packet area being increased 4 times up to 12.8 microseconds. This gives us a much larger multipath tolerance, reduces overhead, and gives us better throughput, making outdoor Wi-Fi more reliable and dependable. 11AC only supported 5 GHz. 11AX will support both 2.4 and 5 GHz, and the FCC is opening up the 6 GHz spectrum for Wi-Fi. 11AX will utilize the 6 GHz unlicensed frequency when it is approved by the FCC, which is expected in 2019. The 2.4 GHz band is especially important because of the number of IoT devices on the market, which is rapidly rising. The end result of the 6 GHz process is that it could make more than 1 GHz of new unlicensed spectrum available. The amount of bandwidth available in Wi-Fi in the U.S. has remained unchanged for more than a decade. The confluence of the new 11AX and the new 6 GHz spectrum may just fuel a wireless industry perfect storm of disruption. Also, for the channel bandwidth, with the 6 GHz band opening up, 160 MHz will become a reality, and 11AX is compatible with earlier 802.11 standards. So in brief, Wi-Fi 6 or 802.11ax is designed for high-density connectivity and offers up to a 4-fold capacity increase over its 11AC Wi-Fi 5 predecessor. With Wi-Fi 6, multiple APs deployed in dense device environments can collectively deliver required quality of service to more clients with more diverse usage profiles. This is made possible by a range of technologies such as Ofdm, multi-user Mimo with 8 uplinks and 8 downlinks, target wake-up time, 1024 QAM, long Ofdm symbol, BSS coloring, and increased frequencies. These technologies will play a critical role in helping Wi-Fi evolve into a collision-free, deterministic wireless technology as the IEEE looks to integrate future integrations of the mechanisms into more wireless standards to support the future of Wi-Fi and beyond.